Welcome to this video. In this video we will be talking about how to develop an algorithm for the Gauss-Jordan method so that by the end of this video you will be able to code and solve a system of linear equations using the Gauss-Jordan method. But before we start developing code, we got to talk a little bit about how do we store matrices and vectors. So here, if we have a general n by n linear system that we from linear algebra can write like a matrix A times a vector of unknowns x is equal to a given right-hand side vector B. If I write this out from linear algebra, we know that we can index each one of these entries by two subindices. The first subindex would give me the row number, and the second subindex would give me the column number in this matrix. This would then multiply a vector of unknowns x, right? That only has one subindex because that only has a different row number for each one of the entries. And then we have another vector b that is our given right-hand side. So how does MATLAB store and deal with vectors? So if we have a column vector, what we do is we just give the vector a name, a variable name b equal to, and then we use square parentheses. And then we basically write each entry separated by a semicolon. The semicolon basically just means go to the next row. So our vector b1, b2 all the way through bn would be having a square outside parentheses, then the value of b1, semicolon, the numerical value of b2, and semicolon, and so on, all the way to the last numerical value bn. So as an example here, if the vector would be 9, 23, 11, we would write this in MATLAB as b equal to square brackets 9 semicolon 23 semicolon 11 semicolon. We'll skip the last semicolon. Now, if we have a vector b, how do we access an entry? For example, how do we access the third entry? To do this, we just use round parentheses and write b round parentheses 3. That would give us the value of the third entry. In the example above, that would be 11. How do we access the ith entry? Well, then we just write b round parentheses I. That would give us the numerical value that's stored in the ith entry of the vector b. How about matrices and arrays in the more general case? Well, if we define a matrix with numbers, all we need to do is write each one of the entries inside of a row separated by a space, or you can use a comma if you want to as well, but a space will do the trick as well. So we would write this matrix up there, the numerical value that's an A11, a space, then the numerical value that's an A12, and so on. And if we want to advance to the next row, we would write the semicolon. So the example here, if we had this matrix, 1, 2, negative 2, 2, 3, 1, 3, 2, negative 4, we would write this in MATLAB as A equal to, again, square parentheses, 1 space, 2 space, negative 2, then the semicolon for the next row, 2 space, 3 space, 1 semicolon, and then 3 space, 2 space, negative 4. That would store the given values here for the matrix A into a variable that's called uppercase A. How do I access the entry in the matrix A that's in row number 1, column number 2? Well, all we need to do is use the variable name, in our example uppercase A, write round parentheses, and then the first index, comma, followed by the second index. How about if I wanted to access the row I, column J entry? Then I would write uppercase A, round parentheses, I, comma, J to access that entry. Now there's two other things that I want to show you. The first one is how do I concat a matrix and a vector, provided they have the same number of rows. Well, the way to do this is you write square parentheses, and then you just write the first object, which in this case would be the matrix A, write a comma, and then the second object that you want to concat, in our example here, that would be the vector B, and that would give me the augmented form concating a matrix to a vector. And then there's one other function that we will need when we code the algorithm for Gauss-Jordan is we need to be able to determine the number of rows and the number of columns of a matrix. Let's call little n the number of rows and little p the number of columns in the matrix. And then the MATLAB command to find these is just size, parentheses, and you pass in the matrix that you want to know, the number of rows and the number of columns of. Good. So those are some of the code elements in MATLAB that we need to develop the Gauss-Jordan elimination algorithm that can be applied to any sized linear systems. So let's do the steps. The first step of the algorithm that we previously developed and did by hand was to go to the augmented form. Let me call the augmented matrix uppercase C, and I'm just going to concat the right-hand side vector B to the original matrix A. So this gives me now this augmented matrix C with all the entries with the two subindices, right? First subindex being the row number, the second subindex being the column number. Next up, I want to actually figure out how many rows and how many columns do I have. And I'm just going to use the size command for that on this augmented matrix C. And now n is the number of rows, the number of equations that I have. And p is the number of columns in the augmented matrix. Okay, so let's dive into the algorithm. The algorithm first did what? It said divide my first pivot row by the pivot entry. Okay, so that means here in row number 1, I want to divide row number 1 by the pivot entry, which is the entry 1, 1 in the matrix C. So I'm going to take the value of C11, and I'm going to divide it by, well, C11, and the result is going to be 1, of course. But I'm going to do this for every entry in this first row. So the next column over, my entry C12 will be divided by this value C11 as well, and the result will be stored in the same storage location C12. And I'm going to do this for every single entry into this row up to the last column P, where then this value of C1P will be overwritten by C1P divided by the original value in the pivot position C11. Okay, so let's translate this into code. So the result of this operation, right, is always on the first row. So if I access my matrix C, my augmented matrix C, the first index is always 1, but the second index goes from 1 to 2 all the way to P. And the way to write this in MATLAB is just to write 1:P as an implied loop that I want to operate on the entire row starting at column 1 going all the way to column P. That's on the left-hand side of my assignment operation. And what do I have on the right-hand side? Well, I have that same variable, right, this same location. So I again have C for row number 1, and all the column indices go from 1 to 2 all the way to P. So I have C of parentheses 1, 1:P. And I'm going to divide every one of these by C11. So C of parentheses 1 and 1. So here's now a challenge question that you can try to answer. This is a code segment that I wrote up there, how to divide this first row by the entry C11. So the question is, I'm going to give you an alternative code here in the box that says that I'm going to do this entire operation as a loop. I'm going to do a for loop for I from 1 to P, and I'm going to do just one column entry at a time. So C of 1, I is equal to C of 1, I divided by C of 1, 1, right? The storage that is in the pivot position. So the question is, does this code produce the same result? Okay. And it turns out, no, it doesn't. And the reason for this is, if you look at what the code with the for loop does, for the very first entry, when I is equal to 1. In the first execution of this loop, the 1, 1 entry will be immediately overwritten, and it will become 1. So now I have in the 1, 1 position the value 1. And all subsequent divisions by this entry will not divide by the original pivot entry, but they will just divide by 1. So this splitting it out as a loop doesn't actually do what we wanted to do, divide the entire row by the original pivot entry. Okay, but first step of the algorithm otherwise done if we use that first code snippet here. And then the next task in the Gauss-Jordan algorithm was to generate a 0 in the pivot column for each of the rows that were not the pivot row. So we have to start with row number 2. So we want to generate a 0 in the C21 position, and the multiplier that we saw when we did the algorithm by hand is just the entry that we want to make 0. So the multiplier is C21. So we are going to store in the location of C21 the original value minus the multiplier C21 times the entry of the pivot row C11. That will turn this into a 0, and we're going to do this now for each one of the entries in the second row, all the way to the last column, so the pth entry, so that C2p becomes C2p minus the multiplier C21 times the corresponding entry in the pivot row C1p. So let's write this into code. So on the left-hand side, we always have the second row, so C of 2, comma, and now my column numbers, they go from 1 to p, so 1 colon p. On the right-hand side, I have the exact same variable, so C of 2, comma, 1 colon p. Now minus the multiplier is always C at the 2, 1 position, so minus C at parentheses 2, comma, 1 times, well, the entry from the pivot row. The pivot row was 1, so times C of 1, going from 1 all the way to p. Okay, good. So that was the second row. Now I have to do this for every other row than the first row. Let's do it for an arbitrary row I. Okay, so I'm going to generate a 0 in the ith row. What's the multiplier? Well, the multiplier is the entry that I want to make 0, which is Ci, comma 1. Okay, so I'm going to subtract Ci1 times row number 1 from the ith row that I'm currently working on. So that gives me a 0 in that first column. And I'm going to do the same operation for every other entry in this row. So I would have I2, the second entry of row number I turns into the original value there minus the multiplier Ci1 times the corresponding entry in the pivot row, which was row number 1. And we do this all the way to the pth column. So let's code this up. So I would have C of row number I, comma 1 to p is equal to, same variable on the right-hand side first, minus the multiplier. The multiplier is C of I, comma 1 times the corresponding entries from the pivot row. That would be times C of 1, comma, and I go for this operations from the first column, colon, to the last column, p. Okay, now we need to do this operation, the algorithm says, for all rows except for my current pivot row, which is row number 1. So if I have to do something for all rows, that kind of leads me to a programming structure that's a loop, right? If I want to do something for every entry, for every row in the augmented matrix. So I'm going to do a loop over every row, and I'm going to skip over my current first pivot row, and I'm going to do this with an if statement. So I'm going to do a loop for I equal 1 to n was the number of rows that my matrix has, and if my current row I is not equal to my current pivot row 1, then I want to do this operation here to generate a 0 in the pivot column. Okay, so that's generating the zeros in the first column. Okay, so we're done with row number 1, the first pivot. Let's do row number 2, the second pivot. First up is we divide the row by the entry in the pivot position. The entry in the pivot position is C22. So we divide the row where we can start now at the pivot position. So we go from 2 to P. We divide this entire row by, starting at the pivot position, by C22. And now we need to generate the 0 in all rows in the second column, except for row number 2. So we again do a loop. We loop over all rows, but we don't do anything. So if I is not equal to 2, right, if we're not in the second row, my pivot row, then we generate the 0 there. And that's the code segment as before, except that we don't do it for the first row, the pivot row, but we do it for the second row, which is now our current pivot row. Okay, so that generates the zeros then everywhere in this second pivot column, except for the pivot row itself. Now let's generalize this, and let's do this for the pivot in row number k, right? An arbitrary pivot in row number k. So the first step that we need to do is we need to divide that kth pivot row by the pivot entry, and the pivot entry is on the diagonal. That's the kk position. So we divide this row starting at the pivot position, right? Everything to the left of that pivot position is 0 anyway, so we don't have to do anything with that. But we divide the rest from k to p by the pivot entry, which is c at kk. And then we do our operations to generate the zeros. And we do this again as a loop over all rows, skipping the kth pivot row. So we have a loop for I equal to 1 to n. And if I, the current row that we're working on, is not equal to my current kth pivot row, then I'm going to do the operation to generate the 0 with a multiplier of Cik. So I get C of the ith row that I'm currently working on, starting at the pivot column K all the way to the last column P. I'm going to take that value and I'm going to subtract from it the location that I want to generate the 0 in, which is row I, pivot column K, times the corresponding entry from the pivot row K, so times C of K, pivot row K, starting at the pivot column going all the way to the last column P, so K colon P. Okay, that generates the zeros there everywhere in the kth, for the kth column. All right, now we now simply need to do this for all pivot rows, right? That's what our algorithm told us to do. We need to do these operations for the kth pivot row for all rows of the matrix. So we're going to just loop over all rows. So we have a loop for k equal to 1 colon n. Remember, n was the number of rows in the matrix. And the first thing that we're going to do is we're going to divide by the pivot entry. Copy paste that code segment over, and then we're just going to generate the zeros in all of the other rows in the pivot column. All right, so that's the entire procedure then to solve a nonlinear system of linear equations. And here I've put the wording of the algorithm that we used by hand next to the code segment that we just developed. So we start out by concatenating the right-hand side to the matrix A to arrive at the augmented form. And we figure out in the code also the number of rows and the number of columns P that our augmented form has. Then the algorithm said for each diagonal entry, so for each pivot in the matrix, we're going to do something. So that translates into a for loop structure for the variable K. That goes from 1 to n, the last row of the matrix. For each one of those pivots k, we're going to then divide the current pivot row k of the augmented matrix C by the pivot entry. That's what this line of code did. And then we did another loop for each row other than the current pivot row, which means we have to loop over each row again of the matrix. And there our variable for the loop is I. And if that I is not equal to our current pivot row k, then we do this. Subtract the multiple of the pivot row, where the multiple is then c at I, comma k, so row I, column k. We subtract that multiple of the pivot row k from my current row I to generate the 0 in the pivot column position. And then the solution will be in the last columns of the augmented matrix. So we have n by n is our matrix. So the first column, that is the first extra column of the augmented form, is in the column position n plus 1. And then the solution will be starting at the n plus first column, going all the way to the last column p. And we can copy this into the solution vector x that will then contain the solution to the system. And that's how you would develop code for the Gauss-Jordan elimination algorithm. Thank you for watching.